Voy a... Muchas gracias. Voy a dar la bienvenida, voy a dar paso, voy a presentar a José Ignacio en español, luego continuaremos en inglés la charla. Entonces, bueno, bienvenidos a todos. Retomamos la serie de seminarios de Quantum
Hola,
Space.
José.
Hola, Germán.
Ahora.
Eh, Nada, después de Navidades y con mucha ilusión, mucho ímpetu, ya tenemos una lista muy interesante de ponentes para las próximas charlas. La idea sea que de momento el martes a esta hora sea una especie de cita más o menos fija, de la gente que lo agendéis. Vamos a intentar intercalarnos para no pisarnos con la iniciativa de PySQT, la iniciativa de jóvenes doctorandos, de manera que, bueno, pues también a esta hora pues haya gente más joven hablando y presentando sus trabajos, o sea que tenemos un calendario que va a estar alternado entre unos y otros, pero casi siempre intentar ser los martes, a veces por problemas de agenda del ponente puede que sea el miércoles. Hoy tengo el placer de recomenzar esta serie después de Navidades con José Ignacio, que es, bueno, lo voy a presentar un poco, pero seguramente absolutamente todo el mundo sabéis quién es, lo conocéis, habéis seguramente escuchado charlas suyas, una persona muy mediática, con mucha repercusión sobre todo en todo lo que tiene que ver con computación cuántica a todos los niveles. Tengo que decir que desgraciadamente no está viviendo en España, no lo tenemos, pero siempre que contamos con él nos echa un cabo. Y desde luego Quantum Spain le debe mucho porque fue la persona a la que encargaron el diseño de lo que ahora estamos intentando poner en pie sus sueños duramente y bueno, estamos muy agradecidos a todo su trabajo y a todo el apoyo que recibimos. José Ignacio es director del Centro de Tecnologías Cuánticas en Singapur, del Centro de Abu Dhabi, como dice en la transparencia, y fundador, y supongo que sigue, de compañía Kilimanjaro, que tiene una relación ahora mismo pues, contractual con Quantum Spain y de la que sabremos más en próximas sesiones, porque bueno, la próxima charla es precisamente a cargo de Kilimanjaro. Nada más, José Ignacio, thanks a lot for attending our request, and we are really eager to hear what you want to tell us about encoding, and the floor is yours for the next 45-50 minutes. Thank you. Everybody is encouraged to ask questions and intervene at any point. Yeah, thank you.
Thank you very much, Javier. Muchas gracias, Javier. I'm pleased. I mean, I don't have that many great things to say, honestly. So, the people that know me know that I hate hype. Actually, my last paper is a paper on hype, on quantum hype, and trying to alert the community that we have to be careful. Okay, we have to be honest. We have to be faithful to science, not to the economical spirits of the time. So as Javier said, I'm talking to you from Singapore, 11 p.m. in Singapore, and I'm directing the Center for Quantum Technologies. This is a place with 153 people. That's really a large institution, one of the largest in the world in quantum technologies. We have 25 PIs. We have over 100 of research lines, including quantum computation, quantum sensing, quantum communication. We have a satellite that will deliver quantum key distribution to different countries. I'm the chief researcher in Abu Dhabi in the Quantum Research Center at Technology Innovation Institute. By the way, Abu Dhabi will have the first tracking station of the very same satellites. So the first communication that we hope to have will probably be Singapore, Abu Dhabi. And then Kilimanjaro, where as I will say, I do believe there is a very natural niche for Kilimanjaro. So let me talk today about quantum computing, but I don't know how to phrase it. I want to be extremely down to earth and humble. Okay, so let me start with the very first comment. It is a fact that many people don't understand, that a quantum computer and classical supercomputers or good computers do not compete with each other. So there is a big difference. A quantum computer might be good for problems with a small data and very intense computation, very, very large computation. Whereas a classical computer, or in particular multi-core, multi-node supercomputer, is good for a lot of data and a small computation in each node. So you distribute the data, each node processes a piece and they communicate to each other. So the nature of the problems is different. So, and this for me is fundamental, because there is, like, people say, oh, the future is of quantum computers will do everything. No, this is not true. Okay. To add 7 plus 4, you don't need a supercomputer. You simply need nothing. You do it. Okay. To do multiplication, you need a pencil. So the instruments that humans are building to compute are adapted to the complexity of the computation. Okay, that's fundamental. And it should be very clear. Quantum computers, small data, intense computation. A big example, factorization. You simply enunciate the problem that you want to solve with only a few bits, 1,000 bits. It's extremely hard to find the factorization. A lot of computation based on very little amount of data. And vice versa. You want to simulate an earthquake, you do it on a supercomputer where each node is actually represented the geometry of the problem, and they talk to each other. They follow the laws. The geometry of the computer follows the laws that you want to simulate. So this is my very first step. Don't be confused by that. Okay, don't oversell quantum computer. It's not a solution for every problem. No way. Okay. So the future, very likely, will combine the two of them in a hybrid computation. And this is why the recent effort, so today I had another talk, and my talk was on hybrid computation, and it was given to the people that have to decide whether they invest in supercomputing centers to have quantum computers properly connected to supercomputers. So this is a statement. You will hear a lot about hybrid computation. I put the picture of Riken from Japan. So Riken has opened a group, and they will connect a subcluster of NVIDIA GPUs to a quantum computer. But today, what I want to tell you is a story I've been working for years, and little by little, every time I get a new result, let me update on the things I've been doing in some years ago. Again, I will repeat it for the nth time. It's very humble, very unpretentious. Okay, so I want to tell you that I'm very, very focused myself on encoding. So if you look at what is a process, a computational process, you think that you have to encode your problem somehow. You have to bring your data, you have to upload the data of your problem. And then you will have to process, you have to run a quantum algorithm. And finally, we have a readout. Of all these pieces, the readout, we have theorems, Hellman's theorem, even from the 60s, that we know that there are some optimal ways of measuring. Okay? Process is the art of building an algorithm. But nobody tells you that the bottleneck for quantum computers is encoding. How do I bring, I upload the data of all the customers, all the clients of a bank, 1 million? How do I do that? Because if I need 1 million actions or even more, to upload the data in a quantum computer, no matter that the processing is fast, it will take the same time as a classical computer, or even more. So if we only focus on the process, we are not seeing that we will not be solving any of the relevant problems, because encoding is extremely difficult. Now, maybe there are ways to bypass that. So the first is that maybe we can encode and process at the same time. No need to separate the two pieces. Okay, maybe there is no such a distinction between encoding, uploading your data, and processing them. Can be mixed. Okay, and or maybe we can encode in much less qubits. Okay, we may have compressed encoding, and therefore we are dealing with less qubits. Okay, those are options. And even there is another fourth option I will not enter, which is that uploading this information, classical information, there is no theorem that forbids it to be fast. There is no law of physics that says that you cannot upload information in a quantum system in a fast way. I love to give the example that was very often presented by Seth Lloyd, okay, that used to give this example. Imagine I have all the data of a picture and I want to upload it to now play in a quantum computer. Okay, there are so many pixels that just uploading pixel by pixel is a mess. Yet I can think that the picture is encoded, okay, in a CD, in a DVD. DVDs are mirrors. So the laser reads, there is a different angle. If you come back, I have a 1. If it doesn't come back, I have a 0. So there is no obstruction to send a single photo and send it against the CD or DVD and getting back and then capturing in optical modes. Okay, so nothing says this is not possible. And actually, with all the interference pattern, I'm capturing all the image. So I'm transferring in one go all the information which is in the DVD into a quantum system. You see, this is a Gedanken experiment. Nobody has done it, as far as I know. But there is no obstruction. I will repeat that there is a physical process where you upload all the information in one go. As a matter of fact, building quantum memory now, quantum RAM, is a very difficult problem as of today. And there are people stating even theorems. One of the latest papers from CQT is about how much you can improve if you do the uploading in parallel. Okay. So this is my first comment. So let me then try to go into encoding little by little. I go one step at a time, a little bit deeper. Well, I will go to variational algorithms. As you know, examples of that are quantum eigensolvers. You have autoencoders, you have classifiers, you have QAOE. All these techniques are variational, and we will go into that in detail. So I'm not talking about any exact secret. I'm not talking about things like Rover or Shor, which are deterministic algorithms. Whereas I'm talking about something that really you don't know how many operations you need for a given quality, okay, for a given fidelity. And this is the one time I will mention, and the only time I will mention Kilimanjaro, the company I'm one of the founders, because the bet of Kilimanjaro is in this world where people are discussing systematically universal computation based on gate secrets. The bet, so the proposal from Kilimanjaro is to build an annealing, a coherent annealing. That is, a coherent annealing means that you do your annealing in coherence time. So you want to have, typically, you cannot have transmont qubits. If you work with superconductors, you are talking about flux qubits. And you want to have long enough wide flux qubits because the interaction really of flux qubit is right away as if you had the spins. So you are using the native interaction. You are not simulating interaction. You are not forcing a control node. It's there from the very beginning. It's a little bit like in the cold atoms, that the great barrier atoms are really acting as spins. So what you need is strong interaction. You need very fast gates. And the idea is really to let physics to do the job for you and controlling the intensity of these interactions. That's an annealer. And as time passes, I see more and more the need of having a good annealer. Okay, I will argue later that many people think that variational algorithms are not in good shape nowadays. Okay, I will argue that later. Now, one piece of information that I would like to put just for the young people that may not be that familiar. You know that there is a theorem. You should know that there is a theorem that guarantees that if you want to go from one point to another in the Hilbert space, there is always a unitary transformation that takes a state into another. There is a unitary. So the question is whether you can approximate that unitary with the product of unitaries, which are the gates. So can I do that? So do we have a theorem that says that this is possible or not? So that's the content of that theorem. And this theorem is called Solovay-Kivelyev theorem. Just want you to know that if you have a dense set of unitaries, call it UI, I can find a set of these unitaries concatenated, so one linked after the other, one U1, U2 up to UK, that approximates the real one, which is V. Okay? Will take you to the same place with an accuracy which is bounded. Okay, the distance between these unitaries, whatever norm you use, is less than D. And what the theorem says is that the number of these unitaries, K, is bounded, or it's the order of log of to the C 1 over delta. So the more precision, the more you need, but it's a log, and on top of the log, the C is bounded by 4. In practice, it's around 1, okay? Of course, the prefactor is an exponential prefactor. Nobody says that. It's an exponential prefactor. So what this theorem is telling you is that if you want to gain precision, once you have a secret, you don't need to go very far. You gain precision very fast. Okay, you may need a lot because, as I said, K has a prefactor which is exponential. The bad thing is that there is not a constructive theorem. It's not telling me what is the correct series of gates. Okay, but we do have a theorem. We know that these exist, and the improvement of any variational quantum secret towards the perfect solution is not an exponential problem. Okay, it's bounded by a log. So this is just for information, because very often these things are not taught in undergrad courses, and if you don't work in them, you may miss them. Now, the idea of variational quantum eigensolvers is simply that it was proposed in 2017 by Alan Spurlock, the founder of Zapata. Okay, and he is in Canada. What he proposed, or what they did propose in this IBM paper, was to propose a set of semi-random gates in such a way that you don't know, you put random, but then you get you read out and you compute a Hamiltonian on the readout. Okay, so you're measuring z, x, whatever. You repeat many times, and you're collecting the data on the correlators. And that is sufficient to estimate the energy, the Hamiltonian. And then, well, it's very bad. So then I go back and I correct all the gates. I change them. I change the angles. I change whatever. And I do that by keeping a classical computer that remembers all the configurations and simply improving. So you do what people call machine learning. And then you may choose your preferred way of doing. You may have supervised learning. You may have learning based on the response on the environment. You may have a neural network reading out the first sets of angles and delivering the next sets and learning how you're improving. So these things have been done, adding a quantum computer with a neural network for improving the parameters. So in this way, it was done. The paper was very famous. It produced a breakthrough, and they plotted these three molecules: the hydrogen, this lithium. I don't know the name of lithium H, and then the beryllium molecules. Of course, there is a lot of cheating in this paper, because if you read the paper, they will tell you that they improved the learning classically on a classical computer on a simulation, and only they did 300 runs on the quantum. Okay, so it was trained classically, not quantum mechanically. And the fact that you finally run on a quantum computer is, it's almost an anecdote that you simply deliver that on a classical computer. Yet it produced an immense amount of attention. We had a method that blindly, supposedly blindly, could solve any problem, in particular quantum chemistry problems. Now, the structure they propose, and that has stayed with us, is the one of layers. And in each layer, you had angles that are one qubit transformation plus control Z transformations by pairs. So in one layer, everybody talks to the nearest neighbor, essentially. And then you put another layer, and as you add layers, you have more parameters, and therefore you have to find the value of these parameters variationally. Note that this method only operates on the single qubit gates in a variational way. All the 2 qubit gates are fixed along the process. Now, if any of you has worked on that, you know for sure that as you add the number of parameters, the classical minimization, the classical optimization is harder and harder and harder. Now, do we know that from other fields, not from quantum computation? Of course we know. Okay? I was very young when I learned, it was the first time that people were doing simulations for quantum chromodynamics, for quantum field theory. And there was a very solid Nobel laureate, Wilson, that introduced the ideas of simulation of quantum field theory. And at that time, all these problems were found. In particular, when people wanted to simulate systems of condensed matter with a phase transition, they learned immediately that the learning parameters were more and more difficult to get. The famous critical slowing down. Okay. Now, this was discussed at length in that time, and there were solutions in particular problems like the cluster optimization, things like that. As of today, every generation needs to tell the same stories. Now, Romeo and Juliet have to be retold in every generation with a new language. So the recent years, people have put a lot of emphasis on this problem under the name of Baron plateaus. So what you see is that if you simply take any of these parameters and you try to take a derivative to look for a minimum, you end up hovering over the space of parameters without finding minimum. You are jumping from local minima to local minima. That is that the Baron plateaus is tantamount to say that the derivatives are essentially consistent with zero or exponentially small, or even really smaller than the errors in the system. And the errors dominate the process and you don't get any. Okay. So as a matter of fact, we cannot find the solution of large problems, even in simulations. We did an extensive analysis with a few years ago with Carlos Bravo Prieto, now in Berlin, José Lumbreras, now in Singapore, Tagliacozzo in Madrid. Okay, and what we did is we took this is a graph for the Ising model. As the number of qubits increase and the number of layers, the depth means the number of layers, increases, you see that the accuracy, which is on the horizontal axis, is not improving till you have enough layers that suddenly it improves. So this is due to the fact that first you need to entangle the system. And when the system is entangled, the refinement takes over. So there are two phases in training a condensed matter system. First, to getting the entanglement across the system. Second, refining entanglement. Okay, and this, look at these plots, it's so obvious. Okay, you have a barrier, and when you pass it, you go. Typically, the barrier, okay, is of the order, in this particular case, of n halves. So the number of layers has to be the number of qubits divided by 2. Still, this is condensed matter, where the amount of entropy you get is limited to be a log. Okay, if you are handling with hard instance of NP problems, the barrier is the only thing you see. You don't get any precision. Okay. Okay. If there were any questions, these were introductions. Okay. So I go ahead with the idea that came up some years ago, and we have been refining several times, and I will try to reformulate it again. Javier may remember I introduced that just before leaving Spain in Santiago. I've been working on that, and many people have come up and have jumped on the wagon because it proved to be useful. The name is uploading. Okay, so let me try to explain what this is. So let's now go to these variational mechanisms and go deeper in understanding why they work or why they do not work. Let me go deeper inside the problem. So I want to take a few test problems. I want to classify. I want to do a variational quantum classifier. That means that I will put data, which is classical data. I will run a quantum circuit, and from the output, I will decide whether the data I got can be classified in a category A or in a category B. And as an example, you can take a circle. The points inside the circle are the category A. The points outside the circle are category B. Or a parabola, or a non-simply connected figure, or multi-classes. The idea remains, I want to put the data on my qubits, then process them, and finally measure and take a decision. That's a quantum classifier. I do it, and I do a simple one with entering x and y into operations, into kets, in the one qubit and in another qubit. I do control not. And finally, I do a single operation on one of them, and I train that to tell me whether the point was inside the circle. I take, I have a bias. If I get 0, 0, I call it inside. If I call it 0, 1 also, 1, 0 also, 1, 1, I declare it outside, for instance. And then by playing with this freedom, immediately I get to 96% of accuracy. Okay. Good. You may wonder why. Well, because a circle has cosinus and sinus. And you know what? Unitaries are exponentials that you can expand in cosinus and sinus. So I'm really cheating because this is a problem which is particularly good for cosinus and sinus. That's why I immediately get very high accuracy. But I'm doubly cheating. Come on, hold on. Let's think carefully. I coded my data in a state, call it psi x. X is the data. I don't care how I encoded that. And then I run variational gains. These are u of theta. Theta are variational parameters. And then I measure. But come on, if I have two data and I want to classify them differently, the secret does nothing, because if I take the overlap of the resulting state after acting with you, and I look at the overlap with another state with a different data, so I want to distinguish them, the two unitaries cancel. So actually, the variational gains are useless. I've done nothing. Okay, I am cheating myself. I was minimizing things, thinking that I was doing something. There was nothing there. Whatever was distinguishable, it was in the original encoding, nothing else. Had I changed the encoding, I would have changed the distinguishability of the states. But I didn't notice that I was cheating to myself. That secret was useless. was not increasing the distinguishability of points. Okay. And this was the central idea. How can you bypass that? Well, you can do the following. Every time I have my data, my gates, I add the data I want to classify. So I may put it in the beginning, but I do an extra thing. I put it in the unitaries. So my unitaries are no longer exponential of angles times sigma matrices. They are the exponentials of theta minus x times the sigma matrices. So I put the data in the gate every time. When I do that, the cancellation I had before is no longer there. And therefore, I'm changing the distinguishability. And therefore, there will be a process of optimization. I will increase the distinguishability of the states. So little by little, I will tune my thetas to increase the distinguishability. So this is what we call it re-uploading, because in every gate in the secret, you again add the data you want to classify. To be more precise, you can do a classifier with a single qubit. So you simply take 0 and forget about the initial preparation, no need for that. The only thing you need are unitaries that contain X. And you do that. You simply do that. And you keep doing. And now I train all these alphas, okay? Then immediately you can see, and you have a table here, that if you classify a circle, you can classify in 3 dimensions a sphere, hypersphere, or you can classify wavy lines, or you can classify 3 circles, and we have several categories. Systematically, as I keep adding layers, and I train them properly on the validation set, I see that I increase systematically the fidelities of my classifier. So it's a very successful technique. If you don't do that, you get nothing, essentially. You remain at 50%. As soon as in every gate you add the data, you automatically have a systematic approach to improve dramatically your classification. And as you can see, you can use a single qubit for many categories, because you're in the block sphere, in the end, you divide the zones of the block sphere as the categories. The Hilbert space is huge, it's a continuum, so you can put as many categories as you want. And you may even have data which have many more variables than the plane, like the hypersphere or whatever. Simply, the gates you are using, well, you may use the first gate for X, Y, and then Z and omega for the next, and so on. So there is no obstruction to build a more complex set of gates. And you may read between lines that if I expand all these exponentials, I have cosinus and sinus, and I have cosinus with alpha 1x, cosinus of alpha 2x, I may combine them, and I may have cosinus squared, and then I may have cosinus of the double angle, and so on. So the flavor is that you are building some Fourier expansion here. And that's why you are better and better, because the concatenation, linking all these gates is tantamount to exploring higher orders of a Fourier expansion. That's what you are doing, okay? But that has to be made precise. So let me come back in a little while. So we perform extensive analysis. I love the first figure on the left. Let me show that to you. This is one layer. And it classifies the yellow as one category, the purple as a second category. The second drawing means in green, you were successful. In red, that was a mistake. So the more green, the less errors you are having. So as you add the second layer, and you see what? You see a line. You're having a hyperplane. Huh? This is a line, but in general, we will have a hyperplane dividing the categories. On the layer 2, I have 2, but hey, they are not hyperplanes. They have a shape. Why? Because this is a non-linear approximant. It is not a linear classification. It's not a set of lines. It's a non-linear. It's just like neural networks do the same thing. Okay, you want to classify data with a linear regression, you are doing lines that cut the space and define what you're doing. In neural networks, you have curvature, and therefore you immediately adjust better. Quantum has curvature. Okay, and after 6 layers, you see even a problem with a non-trivial topology is wonderfully classified. Okay. As you see on the far right, the arrow is the red points, and you see that. You can check that we did the exercise of having a neural network with one entry, hidden neurons in one layer, and final output. And these 6 layers produce the very same result in quality as 100 hidden neurons in the neural network. Okay. Let alone that if one day we manage to have good quantum computers, the energy cost is essentially trivial. Okay, you don't spend energy. Okay, well, the next step we did was to do it experimentally. So this was done with an ion trap with barium as an atom. What is really impressive for me after working with the experimenters is the precision of ions versus the precision of superconducting qubits. It's really, I'm envious, okay? Because Kilimanjaro, Quantum Spain, is betting on superconducting currents, in particular because you can scale better, faster. But I learned to respect the accuracy of these people in ions. You may see here the results, which are experimental results, what you're seeing now on your picture. This is not a simulation. This is experimental results. These are 3 nines in every gate, and just 4 layers. There is essentially very no experimental error. Okay, it's just the error is the number of layers, but not the fact that the experiment didn't work. The experiment worked fantastically well. Okay. And this was done under the proof of Manas Mukherjee and CQT, okay, in Singapore. We classify multi-categories, multi-everything. All the data you see here, all of them were obtained experimentally, not under a simulation. So it's a fact. We have multi-classifiers with an ion, okay, one ion. Well, this year we went beyond that and said, but we are cheating because we trained the parameters on the classical computer. If we never had the classical computer, if we only have quantum computers, as it will happen if we go to 100 qubits, okay? You don't have any way to train, whatever 100 qubits with a classical computer. So if you only rely on data and you look for the minimum, can you do that? And it's such a tough experiment, okay? So here you have different techniques. On the right, you have simulation at the continuous lines, and then all the dots are different techniques to look for the minimum, okay? And the 2 main differences is whether we use gradient descents of some sort, analytical, of what's called, the gate, and you want a gradient, the derivative of the gate is analytical, so it's simply a computation. You can do the computation on the quantum computer, but of analytical derivative, okay? Or genetic algorithms. And by far, in our case, by far, genetic algorithms were better, okay, by far. So the search is amazingly, you have a hint at on the plot of these mountains, which is how the accuracy goes as the number of generations with different seeds. And you see the landscape, and you can have an intuition that this is a mess. Okay, so if you go with gradients, you don't get any. So it's a fact. We just managed to have it done, and it worked. Okay, so we got the very same results. It's gotten by cheating on the classical training of the quantum computer by doing a quantum training of the quantum computer. Okay, there are very, very few papers that go in this direction. Okay, in particular because in the NISQ era, the errors are so big that people are essentially not getting anything on superconducting qubits. This was possible because it was done with ions. Okay, ions is a completely different thing. Maybe it's a good time that I tell you things that are happening that maybe you know. You know that in ions you have ion Q, but you have now a new compounder, which is Quantinuum. Quantinuum is given for free access for a few months to their machines. They are spectacular, much better than ion Q. They get they are getting the 3 nines and they're working on the 4 nines in order to get it. I think Dorcas had the microphone.
Good afternoon.
Can you close the microphone? No? Dorcas? No? Okay. So why this is working? Again, let me go back to neural networks. In neural networks, you have an intermediate. There is a theorem from the 60s that says that one neural network with large enough, one single hidden layer can reproduce any functionality. And if you look now at the figure on the left of the neural network, you see that every intermediate node is asking the value of the external data. So the data are re-uploaded on every intermediate neuron. So we are doing the same thing. We are re-uploading the data in every gate. So what matters is the re-uploading fact. And this is because you are querying it's a query complexity issue. If you think carefully, Grover's algorithm is about how many times I recompute the oracle. So I compute my oracle. It's how many times I'm asking whether this is the solution or not. And as I increase the number of questions to the oracle, I improve my quality. So behind the algorithms like Grover, like variational quantum methods that I'm saying, the hidden complexity is the query complexity. Okay, this is what matters. You can read immediately what would be a tremendous problem is to try to deal with a lot of data, because then I have to query the data, and there are a lot. So how do you do that with a quantum computer? It's not trivial. Okay. Again, there are no theorems that tell you that there are no ways to do that, but you have to be careful. I think I'm very late, so let me speed up a little bit. After that, we also considered why this is happening, and we went to the idea of building up a Fourier series. Well, there it goes. Now, this is the first time I show the explicit form of one of these gates, and you can see here that the values of x and y are there, and you multiply them, and you now tune these things. So you can ask is if I multiply all these gates to a given order and they are of the form of a Fourier expansion, which is the bottom line, what happens if I add one more? And then when I add one more, I can see that I recover the Fourier expansion for every element of the unitary series with one more term, and the combination of the new terms are given. So you can prove mathematically that the reuploading technique is exactly the same as building a Fourier expansion in every term of the unitary. And the more gates you have, the more terms in the Fourier expansion, therefore, the more precision you're getting in your answers. And this we did experimentally with Fondias. And indeed, you have here in black the functions we were training as the functionality of the last output, okay? The probability you read. And we were training two different things, and you can see immediately that it works. Okay. So indeed, as you increase the number of layers, you have a better approximation to the function you want to simulate. Okay, so let me go towards the second part, which are only a few transparencies. But I said in the beginning, I had other techniques. One technique was to combine encoding and processing. I show you reuploading is the technique for that. What about compressing? So it happens that nobody says that if I want to encode a number, an integer less than 2 to the n, well, everybody is encoding in the qubits. Okay. But I could encode it in a continuous variable in a 1 qubit. The Bloch sphere is a real number. A real number contains infinitely many discrete numbers. So why do we use n qubits? It could work in a single qubit that contains the information. So think carefully. When you encode a classical problem into quantum state, you don't have bits, you have qubits, and qubits have 2 degrees of freedom, which are continuous. Okay? So you can encode as much information as you want in 1 qubit. You don't need many. But we do work with n qubits. Why? Why are we doing that? Why don't we use the other guy? Okay, this is a very, very critical question. Okay, you can encode a lot of classical information in a real number. So why do we do that? Okay, I did that many years ago. Let me tell you why I did. I'm not going to a continuum, but have an exponential compression, okay? Not an infinite compression as you have on a real number, but an exponential. I did the following. I took a picture and I declare the picture into a cat in the following way. You divide the picture in 4 quadrants, and if I belong to the first quadrant, my first index, I1, is a quadrat, takes a value 1, or 2, or 3, or 4. Then I divide that in subquadrants. That's my second quadrat, and so on. As I have more and more quadrats, I'm specifying better and better in a telescopic way the pixel I'm addressing, and then I put as a coefficient the level of gray. So this is a simple construction that tells you that the number of degrees of freedom in a picture is tantamount to a ket that has log 4 of the number of pixels in the picture. Okay, so it's a logarithmic number of quadrats. That's an example of a compression which is not infinite, like in the real number, but it is substantial. It's an exponential compression. If I could generate that state, I could send it to you on a box, and you could take it in your place, and you would have in that ket the same information. How you extract that information is the difference here, because every measurement you only get one information. Okay, but I've compressed the information. So I did that with Mr. Feynman. So I took a picture of Feynman and I compressed it in this way, and then I use tensor networks. That's a quantum-inspired compression mechanism. And as I increase the ancilla of the tensor networks, I get a better and better picture, so resembling the one of Feynman. Okay, so it's a technique that you can even use for quantum-inspired. The amazing thing is that as of a couple of years, this idea has taken over the community, and now there are simulations of fluid dynamics, airfoil, using exactly that representation, and taking the ES as a matrix operator, product operator, MPO on the matrix Flourish state. So you use tensor network, and the dynamics is acted as a matrix product operator, and then you do the simulation of how the fluid moves. Okay, and I'm giving you the paper of Leandro Olita, which is very nice, and I couldn't bring here the simulation of the fluid, but it's really spectacular. So although the things I'm showing you now, I've not done them myself, but I think they're worth knowing. And let me go to yet another way of compressing. And let me illustrate that with the max cut problem. The max cut is just a classification problem where I divide the... So it's a problem where we have... It's a problem where we have a set of points we divide in two categories, which are here in green and in purple. And then you have to make them in such a way that if I separate them, I'm cutting the maximum number of lines. That may be difficult, but look at the right example. That is really, you can see the difficulty of that. Because you can place, imagine it would be an ideal problem with half of the points in one category in the other. How many combinations I have when I have to choose n over 2 n divided by 2 points out of n. So this is the combinatorial number of n over n over 2, and this is 2 to the n halves. So it's exponential, the number of combinations. So this is an NP problem. It's extremely hard and has many applications. Well, let me do the following. In the first papers that people try, they classify whether a point was in the category A or B by assigning a qubit to the point, and if you measure more than 0.5, you declare in the category A. If you measure less than 0.5, it will be category B. So you assign 1 point, 1 qubit. What has been done in the last year, and the last 2 years, but in the last year for this problem, is why are you doing that? Why don't you encode the point in a correlator? So what I do is that I choose 2 points, 2 qubits, and then I measure Z1, Z2. And Z1, Z2 is the product of Z1, Z2. It may be +1, -1, okay, when I measure. So actually, I can assign a probability. And simply assign the probability for that to happen. But now it's not a point to a qubit. It's a point to a correlation of 2 qubits. But who said 2 qubits? I can take any pair. There are n over 2 pairs. But then I can associate the Z component, the Z operators, the X operator, the Y operators. So if you think carefully, if you can take 3 correlators of 3 points and so on, given n qubits, if I construct all these independent correlators, what I'm doing is I'm doing tomography, full tomography, and therefore I have the possibilities. So I can encode an exponential number of possibilities into the correlations of quantum state. So this has been done recently, and this is the solution for this problem. The black dotted line is the standard best approximation that people have. This problem in particular, the blue squares are 2,000 points. So you are dealing with a combinatorial problem of 2,000 over 1,000. It is completely out of scale. It's 2 to the 1,000. Yet the variational quantum eigensolver on this encoding works extremely well. Okay. It's beautiful, and there is a surprising fact that in the training, the baryon plateaus are much softer than in the hard encoding. So there is something going on when we work in correlators that we have been missing till now. And this is really, really something we have to go deep into that, very deep, okay? What is the first advantage of not working with 1 qubit and 2 qubit? Or is entanglement? Is the fact that the Hilbert space becomes exponential, is the fact that now, without going to real numbers, still on discrete variables, I now have correlators, and therefore I can encode in a more elegant way a lot of degrees of freedom. So I think this is profound. We have to go there. Okay. So this is it. I'm a little bit late, sorry. But I just wanted to tell you that encoding, not only algorithms, encoding matters. Okay, we have to think a lot about encoding. So thank you very much, and back to you, Javier.
Thank you, José Ignacio. Well, it's been a pleasure, and I'm really asking for interventions and the people asking questions. If you have anything to ask José Ignacio.
I would like to have a quick question. about in the part of the trainability of the quantum circuit and so on, that you mentioned that genetic algorithms were much better than the gradient-based algorithms. I will need to read the paper because that's very interesting. But do you have any quick or I don't know
Yeah,
insight
because
about what's the problem with the gradient-based?
it's just that when you go to high precision, so when you really want to get to the 96% of classification, the error of the measurements are such that you stop learning. So you have a barren plateau due to the error of the measurement. And therefore you get lost. You simply, if you follow the gradient, you go to another place which is not good. Whereas if you keep on the genetic algorithm, there is an element of jumping from one place to the other. That eventually you get in a very good minimum. Okay, you are not floating around. So I keep telling everybody that evolution, we humans, are not the result of a gradient descent. We are the result of genetic algorithms. So there is an element of a very powerful element in genetic algorithms that they are very blind to the landscape, whereas the barren plateaus are essentially due to the shape of the landscape. Okay, one is blind, the other is fully dependent. And in our particular case, it was much better.
Okay, thank you.
I have a general question, José Ignacio. Yeah, I appreciate you try to explain the similarities between the data re-uploading and the natural neural networks, as saying that you were actually doing something similar because all the neurons really need that. Yeah? But there's an essential ingredient in the classical neural network business that is this nonlinear sigmoid function that tells you that suddenly your neuron has the fires because it goes beyond some threshold. I'm looking for is there something similar here? Because the only thing that I can come up which is similar to that business would be something like the collapse of the wave function or something like that.
No. It's exactly the same. The equivalent is the fact that your gates, these are gates, okay, they are exponentials. So the exponential is the nonlinear thing. So cosinus is nonlinear. And
is there something similar to the firing of the?
Yeah. So the firing, so there you have the key element of the neuron an artificial neuron, is that it has to have two regimes: a saturation regime, okay, and a linear regime. So if you want sensitivity, you're in the linear. If you want to saturate, so you don't want further response, you're in the nonlinear. Remember that again, this is happening in your body, the way your ears work has the two regimes and so on. So every decent sensing biological mechanism has a linear regime and a saturation regime. The neural networks, whether you put a tanh or you put a sigmoid, is the same idea. You have saturation versus linear. So of course, a cosinus does the same thing if you work on a piece of it. So you have a linear piece, okay, sinus, and then it saturates, okay, and then you have periodicity, but you have linearity and saturation. So the elements in the quantum mechanics that nature gives you for free are the nonlinearity. So if you think again more carefully, when a neural network is computed, the inner core, okay, what are you doing a lot of times? It turns out that the addition of the weights by the previous guy is a linear operation, which is very easy. So what it takes a little bit more effort is to compute a nonlinear function. You have to take an approximation to that table, okay? And that's how you do it in practice. Here, nature does it for you. So you don't have to do it. When you do the gate, that pulse is a unitary. And therefore, it is built in quantum mechanics, the nonlinearity. Okay, and you can always fine-tune alpha, beta, lambda to go to the place where these cosinus or sinus are in the linear regime, and you don't see the saturation. So essentially, that's why both theorems, the theorem in neural networks and the theorem I show you here, both of them go to harmonic analysis Fourier series, both of them. So you make contact with the Fourier series in both cases. And because Fourier series, there is a fundamental theorem in harmonic analysis that says it's a universal approximant. That's why this is a universal approximant.
Okay. Okay, thanks. I
Germán.
see Germán wants to ask something. Come on.
Yes. Okay, nice talk, José Ignacio. Let me ask you the point, because here you have been playing most of the time with the one qubit, right? Well, a part of it. But then there is not entanglement here.
No.
Okay, so
This is shocking, Germán? There is a theorem of the year 2000. Forgot the numbers. By Vidal, Janet, Yacine, Janet, Vidal, that says, I remember this paper after I did the re-uploading, so I did not quote it before in due time. It says that if you want to distinguish two unitaries in one, okay, the best you can do is the following: is to have only two qubits and entangle them into the maximally entangled state and operate with one unitary in one of the two legs, and then to undo the entanglement. And you can prove this is optimal. And they have the theorem for any dimension of the unitary and every number of copies. So there is an optimal circuit to distinguish two unitaries. So, since you mentioned that, what I was trying to do recently is go one step beyond, and with two qubits, make what would be a discriminator. So the next step would be not to make a classifier, but a discriminator between two. And train the discriminators, okay, to two categories. And then simply set the points in pairs. And I would train the thing to be either equal, and the output is yes, they are in the same category, or they are in different categories. Nothing more than that. With two qubits, this is optimal. And then with the discriminator, and you have a pool of examples, if a new point comes, I simply compare it to every point I have in my database. So I run k times my discriminator, and then I have a new method, which is the vote of the majority, to tell me whether the new point is good or bad. This is like having a new guy in the university. No, you have a committee, and there is a vote, and they say, yes, he can go, or no, he should get out. So it's a discriminator. Okay, so you here put the idea that I'm trying to pursue is that I'm smoothing, I'm ironing out the little defects of the discriminator by the vote of the majority. Okay, that's what I'm trying to do. And I have even the idea of the hyper-selection of the best individual, the guys that never make a mistake. And that would be like the council of the wise men, that if their opinion is that this guy is in this category, please get it. Okay, so I'm trying to complete the idea of classifiers with the idea of discriminators and majority vote.
I see.
These are the theorems that help me to know that I cannot do better than that. So entanglement is overestimated in general. It brings very little. Brings the power is re-uploading, not entanglement.
That's interesting. Yeah, to kind of.
If you have many copies, then yes, you have to entangle all of them. But if you have is a different problem. Is the distinguishability when you have many copies? Okay. So read the papers of Yacine, Janet Vidal, and they cover all the possibilities.
So this is what Javier Mas was saying. The non-linearity comes through this reloading, right? Okay. The resource, you would say, is this non-linearity, somehow to non-linearity.
Actually, I didn't bring here, but we have a very nice plot that as you add layers, you see the points that were coming in different positions in the block sphere, how they are assembled towards the North Pole and the South Pole as you add layers. And this is the nonlinearity pushing some points up, some points down. Whereas a single unitary would rotate the sphere and would never change the distance between the points. So a single unitary does nothing because it's the rotation of the Planck sphere. You need to deform the surface of the Planck sphere. You need to add metric in the surface of the. Okay.
I see. Okay, thanks. Thanks. Okay.
So is there a last question or comment? I think it's been a very nice. Yeah, yeah.
If I could, I don't know if there is another question, maybe.
Another guy who knows a lot is Carlos. You should ask Carlos about this. He has thought a lot. Tell me, Carlos. Carlos Bravo Prieto is an expert in this topic. Yeah, tell me, Guillermo.
Yeah. Sorry, I didn't want to interrupt. So I have just another last question about encoding. This because super interesting. Because generally you have this problem in which you can only encode the information for a classical problem like MaxCat in this way, in assigning the qubits to the states. And I found in the literature some people that made some kind of logarithmic exponential encoding, so you need only a logarithmic number of qubits, but you're still assigning qubits states to the classical states. For instance, for the traveling Silman problem and so on. Problem is that then the depth of the circuit increased like also exponentially, and then it's impossible to treat that problem because of the errors and so on. And in this case, are you trading something which is the, I don't know, the extra cost, or you have to measure many times or something like that?
No, but let me say that the word that we are using in TII, this is done at TII, okay, and we discussed them, is that the naive encoding is like not making use of the Hilbert space. The other encodings, you are making use of the Hilbert space, and therefore you are using the volume to put the things in different places. And you can go exponentially deep, as I did in the images, okay? This is not going that deep. So if you take only the two body, you have n square. If you take the other, you have n cube. So you can put as many powers as you want, and only if you take all of them, it would be exponential. So we believe, internally we use this word, we believe there is a sweet spot. We believe that there is a balance here between not using the Hilbert space or being too greedy, that you want to use everything in the Hilbert space, that then you cannot operate. Everything is exponentially small. You cannot classify, you cannot train, you cannot do things. The fact that the Baron plateaus are softer for these encodings, to me, is telling us something. So maybe we need a figure of merit, like the Baron plateaus, to tell us that we are finding something which is halfway and probably better. Okay? So, in my opinion, there is an optimum. I don't know where is the optimum. So this is one of the first examples that I see these things happening. It's very nice because, you know, the published paper only classified 2,000 points. But internally, in the efforts we have been doing, we had the max cut for 7,000 points. This is outrageously difficult for any classical algorithm. And you're getting decent results here. So, you know, for one time, I would like to explore that much further. Believe me, encoding is a big thing. It's a non-trivial thing, okay?
In a way, how to do it intelligently, because it's kind of frustrating having a very small classical problem and needing a monstrous number of qubits. So that's very promising for sure.
This was,
okay.
The pictures were obtained. I didn't say that, but these points are in a real computer. Okay, so it was done in IonQ with 17 qubits, the 2000, and 13 qubits, the 800. So these are real data. Okay. Yeah. So.
Very good. Excellent. So I think it's time to thank José Ignacio warmly, and goodbye, everybody. And I expect you're back here next Tuesday. Next Wednesday. Paul Forn is going to give us a seminar, and a very interesting one. So thank you, José Ignacio, and goodbye, everybody.
Bye bye.
Bye.
Ciao, ciao.